In this video, I'm going to talk about the different approaches of upgradable contracts on the Ethereum blockchain. The topic of upgradable contracts is nothing particularly new to the Ethereum world. The problem is, no matter the implementation, there is always a drawback and an advantage. Now, in general, there is a good reason for and against upgradable contracts. The most important aspect against upgradable contracts is immutability. It's this element of trust that nobody can change anything on chain, right? It's like burning the logic into the blockchain. So once you release your code, bam, it's there, it's on the chain and nobody can change it. Not you, not anybody else. But on the other hand, the recent hacks were all based on very simple programming errors. We saw it with the Parity wallet, or we saw it at the beginning with the DAO that led to the hard fork of the Ethereum chain. Those bugs could be fixed very easily if there was a way to just upgrade the smart contracts. Let's have a look at the first very intuitive approach. We release a new contract and move all the data over. For example, this very simplistic contract that stores a public unsigned integer myvar. I will walk you step by step through this smart contract now. There's one public unsigned integer myvar. There's the constructor of this contract which stores the unsigned integer, and then there is one getMyVar function that is also public and is a view function and returns myvar. All in all, very simple. Let's run this. I go to the run tab and I create this with let's say 14. I hit create, and myvar, because it's a public, we already have a getter, but I added another getter, which is a view function, getMyVar, it returns 14. Now, what if we want to change the getMyVar function so that it returns 5 times myvar, like this, 5 times myvar? We could just release a new version of some contract. We could read the variable myvar from the old contract first and then set it in a new version, right? But there are some problems with that. First of all, what if we release a new contract but make a mistake during setting the variables? And with only one single variable, it's all pretty convenient. But what if there are hundreds or thousands of variables? Well, it's easy to see that this doesn't scale well if you have 100 different variables, and it's also not very trustworthy. Now, another intuitive approach would be just to have the logic separated and import it into a bigger main contract and use it from there. Let me give you an example. We have one user library and a struct in that user library called data storage. And inside the user library, we have all the logic for username exists, for example, and set username. Inside the user contract, we have the userlib data storage as our data storage. So we take this data storage from userlib as our data storage here inside the contract. And then we're also using the userlib for the address. So for example, we have then two functions, is my username registered or register me, where we can just call directly on the message sender address the username exists with the data storage, and it will come here to the library address self, which is this one, and then the data storage, which is this one that we give it over here, and it will basically just return the boolean that is set inside the data storage. Set username, pretty similar. We can directly call on the address set username data storage, and it will come here. We have the address as the first argument and then the data storage as the second one, and then we can just set it. Does it do anything useful? Probably not, but for the sake of this example, just bear with me. Now, the problem is if we are trying to compile this, and I'm gonna show it to you over here. If we are trying to compile this contract, or if we're going to try to deploy this contract, then you can see that directly inside the user contract, we have a placeholder for the library, and this is where the linking happens. So the linker would go in there and put in the library's address at the exact position where I just showed you the placeholder. Now, intuitively, we want to upgrade the library to a newer version. Let's say we want to change here that set username also has to have some checks if the user is already registered. Now we can't update the user contract anymore because the address of the old library is already fixed in the bytecode that we are deploying. Now, before we dive into our own solution, let's have a look what's already out there. First of all, I want to start with Monex.io. They are a great intro into upgradable contracts based on the larger series of in-depth but older Solidity tutorials. Those tutorials are very well written for larger scale architectures. They resemble what software architecture is all about, making it abstract where necessary, upgradable, reusable, and so on. The second one I want to talk about is the proxy contracts from Zeppelin. Zeppelin Solutions uses a user-facing dispatcher contract that talks to an underlying library with assembly. It tricks the transaction initiator into talking to an actual fallback function and then delegating the call to a library. You can see that here. So the user transaction comes in to the main contract. In the main contract, there is a dispatcher, and the dispatcher has a fallback function, and then it goes to the library. The drawback: this dispatcher contract must know the memory size of the return values. So if we have return 1000, then it must know this return value in advance. Not the value, but the size of the value. The third one I want to talk about is the Ether router. Ether router is another method. It's quite similar to the Solidity proxy solution from Zeppelin. The one who initiates the transaction is actually talking to a fallback function from the Ether router. So it basically looks like this. We open the contracts, we go to the Ether router, and you see there's one fallback function, and then there's an assembly part which makes a delegate call to a resolver. Now again, you have to know in advance the size of the return value, or else it cannot load the correct size into the return variable. Then there's this blog post from Elena Dimitrova, which describes the best technique in my opinion. Instead of trying to outsource the logic, you put the storage somewhere else. The idea is rather simple. There's one smart contract called Eternal Storage, which is a pure storage contract without the logic. And then there's another contract which can access the Eternal Storage contract. And this encapsulates the logic out of the contract that is facing the user. You can have as many contracts accessing the Eternal Storage contract as you want, and hence update the logic part without sacrificing the storage. The last one that I want to talk about is a follow-up post based on the blog post from Elena. The Eternal Storage is also not flawless. It was introduced before the Metropolis hard fork. Before the Metropolis hard fork, it wasn't possible to interact with dynamic byte size arrays such as strings, so this follow-up post fixes this. And they have a different approach here on medium.com/rocketpool/upgradable contract design. And they took this Eternal Storage and based their own Rocket storage on this. Rocketpool is laying out how they use the Eternal Storage introduced in Elena's post to power their infrastructure of upgradable contracts. They posted the improved version of the Eternal Storage, which can now save almost anything you like. But what's behind upgradable contracts? Let's have a look at our very simple example from before for saving users. In this example, we take again our user contract and we are going to outsource the storage part from the actual logic part. We have two contracts here, one user storage and one user contract. The user storage has only logic to store data. It doesn't do anything else. The user contract has the logic that interacts with the user storage. Well, there isn't much logic in there yet, but if, let's say, we were to update the logic, we can update the user contract without losing the data or need to migrate the data. The user storage has one mapping where it maps the address to a boolean. And then it has two functions. You can either write to that mapping or you can read from that mapping. Now let's see what happens if I run this contract. I first have to create the user storage. I create the user storage. Let me close this one here. I create the user storage and I copy the address of the user storage and I create the user contract, again in quotes. And now I have my username registered here. This function calls the user storage get address set, which is this function here, and this returns the boolean of this mapping. Now I click register me, and now it's set to true, because if I click on register me, it calls this register me function of the user contract. The register me function of the user contract calls the user storage set address set function with the message sender object, which is my address here where I send the transaction from, and sets the address set to true. So it will call this function here in the user storage. The user storage will set the address set mapping for this address to the boolean I give it here. Now obviously everyone can do this, so we might want to change the overall behavior so only our user contract can read or write. We could add a new mapping, for example, that stores who has access. I could add a modifier and I could call it platform, so that only, for example, platform public is allowed to have access. Let me show you what I'm doing here. Now I have an updated user storage contract and I have a new mapping called access allowed. And on creating this user storage contract, I add access allowed to the person who actually deployed this contract. I have one modifier called platform that requires that the access allowed is set to true for the address who is calling this contract. I also have two new functions, one to allow access and one to deny access for a specific address. And I have this modifier platform, so I could just call it function allow access and then platform public. So everyone within the platform who is allowed can access this function. Also for the set address set that we had before, it's now platform public, and you guessed it right. Once I deploy this contract, I have to add the address of my user contract here to allow access in order to let the user contract write into this address set mapping. Let me show you how this is done with a simple example. I close these here. I deploy the user storage. I copy the user storage address. I go to the user contract. I deploy the user contract with the user storage address where I just deployed the user storage. And now I have to copy the user contract and allow access to this user contract in order to let register me access set address set here in the user storage contract. Now I can call this, and my username registered will turn to true. Because I call the user contract calls the user storage, so the message sender will be from the user contract, and then it will call this address set, and the address set will be set to true as we had it before. Now let's see what happens if I deny the access. It will lead to a virtual machine error, a revert, because here the modifier require access allowed will be false, and this will throw an exception. Now that we have the general structure in Remix, we can go ahead and try to implement that in Truffle. But first, let's install Truffle if you haven't installed it yet. Truffle comes as a node package via the node package manager npm. You need to install Node.js, which includes the node package manager. Then you can install Truffle via the command line. On Windows here, I suggest you use the PowerShell, and I can just right click into any empty folder. And if I hold the Shift key while I right click, then it will pop up an open PowerShell window here. So this will give me a PowerShell window, and then I can just type npm install -g Truffle, and it should install Truffle 401 fairly quickly. Yeah. The second thing that I want to do in this empty directory is I want to use the Webpack project from Truffle, which comes with a MetaCoin example, and I can do this by Truffle unbox Webpack. And this will download the Webpack repository from Truffle and unpack and initialize it here in this directory. Once this is finished, it will give you an output of the available commands, and we are not using anything of this. We are using the Truffle developer console, which is Truffle develop. And then it will open up what you maybe have seen before with test RPC. It will give you 10 sample accounts, and you can, for example, do Truffle migrate. I apologize, actually it's just migrate, but Truffle migrate works as well. So fine. It will compile these contracts and migrate them into this test chain here that it opens up when you open the developer console. Now in this section, we are going to edit the MetaCoin example that comes with the Truffle Webpack project. Let me open up this project in Atom here, and let me open the MetaCoin example, and let's identify where variables are stored. Luckily, in this MetaCoin example, we just have one mapping with the balances where actually variables are stored, and let's try to outsource them into another contract, and I will call this contract, MetaCoin storage Solidity file. I will use the contract from our user before and just change it to a mapping with the balances. So there is pretty much everything here is the same as our user storage contract we were discussing before. The only thing that changed is I have a mapping with balances here, and I have two functions. That is for getting a balance, which is a view function, and for setting a balance, which is a platform only public function, which sets the balance for a specific address. Now, also in the constructor, we are setting the balance to transaction origin 1000, and I will explain you later why we have to do this. Let me save this first, and now let's change the MetaCoin example to use this MetaCoin storage instead of the balances mapping. First, I remove the balances mapping, and then obviously we want to add a MetaCoin storage instance here. And in our constructor, we are going to set the MetaCoin storage contract address right once this MetaCoin contract is created. So we create this MetaCoin contract, we give the MetaCoin contract the MetaCoin storage address, and in the constructor, we set this MetaCoin instance correct. Now also here in SendCoin, we have to change everything that is calling the balances. And in this case, it's very easy because we have the access to the MetaCoin storage where we can get the balance of the message sender. And if it's smaller, then return false, and then set the balance, reduce the balance on the one side, and increase the balance on the receiver side. Also here get balance in ETH, it calls the get balance, which is this function down here, and this function down here has to return obviously from the MetaCoin storage the balance. Now let me introduce a small little bug here, because maybe we were doing some testing and we ignored this bug now for a while and then come back to it. Before we go ahead and fix this bug, I want to show you how you can actually do the migrations within Truffle. Now let's talk about deployment of these contracts. First of all, we need to deploy this MetaCoin storage contract. Then we need the address of this MetaCoin storage contract in order to deploy this MetaCoin contract. And then we need the address of this MetaCoin contract in order to give it access to the MetaCoin storage contract, here allow access. So this will be a 3-part deployment process, while we just need one more migration. I will copy this migration here, So first of all, we want to deploy the MetaCoin storage. This is fairly easy. We just need to require this artifact and then deploy it. But here it gets a little bit more complicated. First of all, we also need the MetaCoin storage artifact. But in this case, we can access the MetaCoin storage artifact's address because it was already deployed in the migration before. And in order to deploy something with constructor parameters, you just call deploy, and then the artifact that you want to deploy, and then the constructor parameters one after the other. In addition to that, once this deployment is done, you can get a promise back, and this is where you can call then. And that means you can get the MetaCoin storage deployed instance as you do it normally in your very normal Truffle contract on the website, Web3 side, on the app side here, and then just use MetaCoin deployed, and then you get an instance, and then you return the instance, allow access from the MetaCoin address. So again, what are you gonna do? First, you deploy the MetaCoin with the MetaCoin storage address. Then once this deployment is finished, you call the MetaCoin storage instance and you allow at this MetaCoin storage instance address for this MetaCoin contract. Essentially, we want to achieve 4 things. Well, first, we want to deploy our user storage only and only if it wasn't already deployed before. Because if we deploy it again, we basically lose all of our data. Second, we want to deploy the actual user contract. Third, we want to link them together. And fourth, if we have a website for our distributed application, we obviously want to update the address for the new user contract that has the logic in there. And here we are back at the MetaCoin example where I said we have this problem with the balances. And the problem with the balances is if I want to set the balances during the MetaCoin constructor, I would have to have access already to the MetaCoin storage, which I don't have because I would have to set first the allow access function here with the address from the MetaCoin example, which I don't have, before it's not already migrated, before it's not deployed. So this is the reason why I moved over these initial balances of 10,000 over to the constructor of the MetaCoin storage. Now I go in again and migrate this. Now let's run a command directly here on the Truffle developer console to see how much balance we have in our first account. I call this MetaCoin.deployed, then I get the instance, I return the instance, get balance, and this is a call from my first account, and then I get a big number object back and I return the big number object to number. So what I would have is 10,000. Now obviously here it's 10,010 because we introduced this little bug here, which we will forget for now, and let's assume that we haven't found this. And we released our code, and then people start sending coins around. Let's say people start sending already coins around, and people start maybe sending 5,000 coins from one account to the other, which are not in my possession. Let's assume that I don't have access to all of this, and it's a bigger contract that is already released. So the coins are sent, and if I call this now, I have only 5,000 coins left. They're already distributed. Things are happening on the blockchain. Things are interacting with my contracts, and I figure, oh my God, there is a bug. So what I'm gonna do next? I would have to fix this bug. Here it's fairly easy. I just save this. But how can I make sure that only my MetaCoin Solidity file is deployed? So only my migration here is running. I can type in migrate-f and then the number 3 for the third migration. And what I see here now is that my storage is perfectly safe. So the amount of balances that are stored in the storage is still there. I just updated the logic in my MetaCoin contract, and because it's working with Truffle, it will also update the contract's JSON file here, which is used by the app. And if the app is loaded on the website, it will use the updated address from the updated MetaCoin example, and it will work just fine. All the logic is there and all the logic is fixed. What are the benefits and drawbacks? Well, after several $100 million stolen because of those simple programming errors, it obviously makes sense to have upgrades in smart contracts in one way or another. The problem is the drawback. If it's not implemented the right way, you still have to have that trusted entity, that person or organization that you have to trust in order, to make these upgrades. One thing to keep in mind, all these upgrades, all the technology, everything around Solidity and the Ethereum ecosystem is very new. So there's a lot to come. There is no one-fits-all solution. And maybe one time we have multi-signature upgrades or votings on upgrades, or only upgrades if a certain amount of people have voted for an upgrade that it's okay. So who knows what's coming next? Maybe the Ethereum platform itself will introduce something to upgrade smart contracts, or we have a framework of doing that in the near future. Who knows? Architecture-wise, Solidity and the Ethereum platform are reaching a point where upgrades are possible. Obviously, there is no one-fits-all solution yet. Sometimes it makes sense to have a very complex storage layer. Sometimes it makes sense to have something very simple. That all depends on the software architect who is behind writing the smart contracts. Well, this is the end of the video. Thanks for watching. Hit the subscribe button and maybe I'll see you in the next videos.